Bienvenido al 51 Congreso de Investigación y Desarrollo, la plataforma anual en donde se comparte el conocimiento y se distingue lo mejor de la investigación científica y tecnológica que se desarrolla en el TEC de Monterrey. Desde el 2020 atravesamos por una pandemia que está originando muchos retos. Para el TEC de Monterrey, la investigación es ahora más indispensable que nunca y el talento científico de nuestros investigadores es una parte medular de la institución, pues las contribuciones impactan de manera positiva en la comunidad. Pero, ¿cómo nos hemos reinventado para dar continuidad a la labor científica?
Ante los grandes retos que estamos enfrentando con la pandemia, las y los investigadores del TEC hemos continuado con nuestras actividades de investigación, adaptándonos y encontrando los caminos. Todo gracias al compromiso que sentimos y al apoyo de la institución.
En este tiempo de grandes retos, los investigadores nos hemos reinventado y adaptado, porque nuestro compromiso y nuestra pasión siguen siendo contribuir a la generación de conocimiento. Deseamos encontrar nuevas soluciones a los problemas de nuestra comunidad a través de la investigación.
Trabajar en investigación y generar conocimiento siempre ha sido una actividad retadora. Pero en los momentos en los que estamos viviendo, los retos se vuelven más grandes. Y son retos a los cuales debemos enfrentarnos con mucha entereza, sin bajar los brazos. Se puede seguir avanzando en el conocimiento. La sociedad requiere de estos avances del conocimiento. Busquemos las formas, las colaboraciones para hacer que nuestra investigación ayude a resolver los grandes problemas de la humanidad.
Ahora más que nunca, los investigadores del TEC hemos generado y adaptado nuestros proyectos para buscar soluciones a los nuevos retos que está provocando la pandemia. Esto significa que el impacto de la investigación sigue trascendiendo. También hemos reforzado nuestra capacidad de adaptarnos y de seguir descubriendo, aún en la adversidad.
Y es que en la adversidad los retos se magnifican.
Y es cuando descubrimos de qué estamos hechos.
Por eso, hoy más que nunca, en el TEC de Monterrey,
seguimos haciendo investigación que transforma vidas.
And before we start this conference, we will see a video of him.
Professor Bulovich completed his electrical engineering, BSc, and PhD degrees at Princeton University. He directs the Organic and Nanostructure Electronics Laboratory, co-leads the MIT NE Solar Frontier Center, leads the Tata Grid Edge program, and is the founding director of MIT.Nano, MIT's new nanofabrication, nanocharacterization, and prototyping facility. He is an author of over 250 research articles and is recognized as the top 1% of the most highly cited in the Web of Science. He is an inventor of over 120 U.S. patents. The three startup companies Bulovich co-founded jointly employ over 350 people and include Ubiquitous Energy Inc., developing nanostructured solar technologies, Cativa Inc., focused on development of printed electronics, and QD Vision Inc., that produces quantum dot optoelectronic components. For his passion for teaching, Bulovich has been recognized with the McVicker Fellowship, MIT's highest teaching honor.
To join you, it is an honor to have a chance to talk to my colleagues at Monterrey Tech. I have indeed thought of this privilege for a long time, and I'm absolutely delighted to be able to join you for this Congress. My topic for today will be to focus on the strength of nanotechnology in defining of what the future will bring. Indeed, simplistically saying, future will be measured in nanometers. I hope that through the slides, pictures, words, and answers to the questions you might pose me, I'll be able to paint for you a picture of an opportunity Indeed, industries of tomorrow are made from nanoscale elements. Being able to control those nanoscale elements can dramatically change the well-being of the planet as we know it. And at MIT, we spend our time asking questions on who are the best partners to work with in order to be able to bring those next set of ideas forward. Monterrey area and Monterrey Tech in particular are indeed those partners we are absolutely delighted to call as close colleagues that we had a chance to work with and intend to work with for many years to come. Let me show you some views of the nanoscale that you might have not necessarily thought of as being nano. So here's an example of gold and silver. Now, gold and silver that you know doesn't necessarily look like this, like these images show. What you're looking at is at gold and silver nanoparticles, little chunks of gold and silver that are swimming in a liquid, ethanol, methanol, water, some sort of solvent that is made out of colloidal solution of nanoparticles within. Now, these nanoscale elements of gold and silver don't look like typical gold and silver. Indeed, if you make gold very small, it will look reddish. And so the images on the left, these vials contained little nanoparticles of gold. Nanoparticles of silver provide blue hues, reflect blue light. The difference between different nanoparticles in the vials, one is the chemistry, gold or silver, but two is the size. Are these particles 10 nanometers? Are they bigger? Are they smaller? Depending on their size, they will actually come up with a different reflective spectrum. Now, I should define one thing. How big is a nanometer? Well, a simple way to put it is if you take your hair, the width of your hair is 100,000 nanometers. So 100,000th of the width of your hair is the dimension that defines the world in which we live. And indeed, we can control it. The tools of today and the knowledge we have allow us to invent that next nanoscale opportunity. The nanotechnologists of a few years ago have indeed used nanoscale in a very special way. A few years ago could be the Middle Ages, 15th, 14th century. The nanotechnologies of that time would take gold and silver melted together with glass and in a process generate nanoparticles of gold and silver embedded in the piece of glass. If the nanoparticles were made of silver, the blue hues would appear on those windows. If the nanoparticles were made of gold, the reddish and yellowish hues would appear. Indeed, the nanoscale defined the coloring of those stained glass windows. And that nanoscale forevermore will maintain that color as the nanoparticles reside inside those pieces of glass. If you're a nanotechnologist of today, you will realize that the same nanoscale property of gold and silver could be used to give you an entirely new way of doing medicine. Professor Lee Gerke uses silver nanoparticles to accelerate detection of Ebola, West Nile virus, dengue, Zika, and COVID-19. Nanoparticles of silver that are dressed with molecules on the outside of the particle, and those molecules happen to be exact matches for the strands of DNA that might be inside COVID, would allow you to go ahead and attach those strands of COVID to the molecules on the outside of the nanoparticle. What that would do is change the size of the nanoparticle of silver, making it just slightly bigger. Whenever the COVID attaches, the particle, you can think of it, grows. And the electrons within that particle start delocalizing. That delocalization yields the changing color of the nanoparticles. So by taking the nanoparticle, putting the right kind of molecule on the outside, you can select what viruses are surrounding that nanoparticle. The way to actually do the experiment is take a piece of paper, paint it with these nanoparticles, go ahead and put just a little bit of blood, a drop of it, on that paper. Paper is a microcapillary medium through which blood will diffuse. If it reaches the nanoparticles, it will bind and the color of the particles will change. And you would know that that particular virus was in that drop of blood. Result is in a very rapid and very inexpensive medical diagnostic system that hence allows very rapid detection of diseases. When it comes to dengue fever, for example, appears, let's say, in a remote part of Africa, the only way to know that and stop the spread of the dengue fever would be to go ahead and go to the village that might be a day walk from the neighboring town and come up with a way to draw blood from the villagers, take the blood, put it in a refrigerated unit and bring it to the town a day later, analyze it and then bring the results back into the town. That is what usually is done without these rapid tests. With these rapid tests, you take pieces of paper with nanoparticles on top of those pieces of paper, bring it to the village, put a drop of blood, and 20 minutes later, you will obtain the result, telling you which villager is and which isn't exposed to a particular virus. Dramatic change in the way we think how medicine can be administered, thanks to the advance of nanotechnology. Indeed, COVID-19 is an example of the nanoscale object that we are battling today. Solutions for COVID indeed also rest on the nanoscale. Vaccines that are right now stopping the spread of COVID are indeed nanoscale molecular elements. And it is the design of those elements that's the key, down on the nanoscale, to coming up with ways of solving the present pandemic. The virus itself might be 80 nanometers. The actual approximate strands that are indeed in the medical solutions are in the scales of tens of nanometers. The virus stoppage by the mask is indeed able to stop objects that are 300 nanometers. So this is the world we live in. It's the nanoscale world. And the solutions and opportunities in the nanoscale world are also made of nanoscale. Any medicine you ever took happens to be nanoscale in size. And so the way to show it is to show you a scale bar. I usually take a benzene molecule, as it is a simple 6 carbon, 6 hydrogen item, happens to be about 1/3 of a nanometer in size, 1/3, 0.3 nanometers. That molecule, let me compare it to typical medicines you might have encountered. Aspirin, ibuprofen, vitamins A, B, C, and D, even drugs like cocaine and LSD. Every one of these drugs, vitamins, medicines, is an object that is very comparable in size to benzene. Take a look at aspirin. It's maybe about 3 times the size of benzene. Hence, it is about 1 nanometer in size. Controlling the spread of the diseases, coming up with cures, are nanoscale science and technology that we can now master, we can truly understand. The size of your DNA is similarly nanoscale in size. Now, we didn't know that first times we started thinking about what's inside our cells. Back in the late 1800s, there was the first exploration of what might be inside a human cell. And we waited till about 1950s to see the very first images of these twisted molecules, what later on we called DNA. The first images looked very strange. They looked like this cross pattern of spots, a diffraction pattern highly unusual and suggestive of possibly some sort of unusually twisted molecule. Indeed, eventually, this particular idea and discovery led to the Nobel Prize for those chemists who suggested that DNA does exist inside the cells. But it took many, many years. It took 84 years of human research by hundreds of people. Today, because of the tools that we now finally have in our hands, we can tell to a graduate student, take a cell, break up the cell wall, pull out the middle of it, put it under a microscope, a scanning tunneling microscope, STM, and take a look at what you're going to see. And a student will see the image on the right, a twisted molecule with a leather-like structure. Indeed, the work over 84 years by hundreds of people gets boiled down to the work of one graduate student over one afternoon. Because now finally, we have the tools to see the nanometer scales and recognize that your DNA is only 2 nanometers in width, opening up entirely new ways of thinking about medicine. Inside MIT Nano, the facility that I have an absolute privilege of governing, running, directing, and indeed guiding together with my colleagues, are instruments like these. This is a cryotransmission electron microscope that allows us to see down to an exquisite detail how biology is put together. This instrument requires an extremely quiet space. No electromagnetic noise, no mechanical noise. You need to cool down your sample to extremely cold temperatures, hence stopping the biological objects from wiggling as you're imaging them. And the result is that you will be able to reconstruct the way biology looks down to the atomic scale, giving you images like the one here on the right that shows you a protein and how it's folded with every one of these little nooks representing an atomic species that forms that particular protein structure. If I'm to come up with a medical solution, I need to come up with medicine that fits like the key in a lock inside this particular biological object. And hence seeing the biological object beyond knowing its DNA sequence is the key. DNA sequence is extremely important, but mechanical shape of how that particular protein folds is the absolute key to knowing how to design medical solution that will be able to fit and hence solve the medical issue I'm trying to resolve. Anything you ever smelled is also made of nanoscale. So again, I show you the picture of benzene to help us figure out what is the scale bar of what I'm about to show you. Here are images of different molecules that generate scents of lemon, of orange, of raspberry, of bananas, grapes, roses. Notice that every one of these molecules is comparable in size to benzene, maybe 3, maybe 4 times bigger than benzene. Again, each one of them is 1 nanometer in size, or just thereabout. Well, wait a second. If I can smell lemon, or orange, or rose, those scents leave the lemon, go through the air, and eventually get to my nose. So it must be that inside my nose, I happen to have nanoscale receptors. And the answer is yes. You're designed to smell nanoscale. The reason why smells are as small as they are is because the smaller the molecule, the less van der Waals bond it's going to have to the neighboring species. And hence, it's going to be able to quickly fly off of the object it comes from, become volatile in the air, and reach your nose. And through that, be able to inform you of the presence of a particular scent in your vicinity. So you are designed as a nanoscale detector for scents. As a matter of fact, if you can distinguish between a smell of orange and a lemon, notice those 2 pictures are actually very similar molecules. They're nearly identical. The only difference is that in one case, the molecule is bent out and the other one is bent in. The chirality of the molecule is different, yet the shape and the chemical species are exactly the same. If you can smell the difference between the orange and the lemon, you are smelling the sub-nanometer difference between those molecules. You are designed on nanoscale up. Now, my colleagues around MIT recognize the opportunity in smelling nanoscale for the sake of recognizing ways of preventing fruit rotting. If I could smell ethylene, a very small molecule, it's drawn on the lower right. It's a plant hormone. It's emitted anytime bananas are ripening, apples are turning red. anytime fruit ripens, there is a strong emission of ethylene. If other bananas smell that ethylene, they will turn from green to yellow. They will ripen as well. Ripening process is triggered by the presence of ethylene, and ethylene is made by the ripening fruit. So if I could recognize the presence of ethylene in the air, maybe I'll know what crate of bananas or apples is ready to be sold from my warehouse. In the United States today, about 10 to 15% of all of the vegetables and fruits rot in the warehouse, because those who have them in the warehouse do not realize that particular crate is ready to be sold. If I can smell every one of those crates, and my nose is not good at smelling ethylene, but if I can make an electronic nose, that would be a transformational opportunity. And that indeed is what Professor Tim Svager did and launched a startup called C2Sense. C2Sense takes carbon nanotubes, puts on those carbon nanotubes molecules that are able to selectively bind ethylene. If ethylene is in the air, it flies by these nanotubes. It will bind to the nanotube and change the resistance or conductance of the nanotube. Measuring the resistance of those tubes will let you know if ethylene is in the air. How do I put down those tubes? Well, you make an emulsion of these carbon nanotubes. You take a paintbrush and you paint it just like this between these electrodes. What are these electrodes on? Well, all this is a piece of paper with thin layer of gold that serves as electrodes, and then hand-painted nanotubes right on the top. That is one of the most exquisite ways of making an electronic nose that can detect presence of ethylene. It is indeed being used in orchards for detection of the ripening of apples, hence saving a lot of money to industries that choose to apply it. Besides ethylene, you can detect ammonia to make healthier styes for animals, or many, many other nanoscale elements, and hence be able to transform in the way we think of what smell will be able to detect, in this case, directly electronically. TNT is another smell that would be extremely valuable to detect, because TNT is a component in explosives. Presence of TNT in real world indicates the presence of a bomb. There is a way to actually detect TNT. It's a nanoscale object. It happens to be extremely strongly electronegative. And if it lands on a surface of a luminescent film, like this one, after TNT lands on it, the film will stop glowing quite as brightly. If you can detect the small amount of brightness change, you'll detect the presence of strongly electronegative material that's most likely TNT if you're testing it in an external environment. That small dimming becomes an extremely sensitive probe of the presence of TNT in the air, actually as good in detecting the explosives as the best other technology that's available to us, which is the dog. The dogs are the most sensitive probe for the presence of explosives. This technology matches the dog. And we have shown that we can 1,000-fold improve upon it by taking this very same phenomenon, and rather than looking at luminescence, looking at lasing action in these films. Lasing is an amplification of any event, good or bad, and as a result can amplify the presence of the bad species, in this case TNT. This is another way to make an electronic nose, and indeed it has been again applied through the use of this FIDO instruments. Company called ICS Pneumatics, now FLIR, has indeed adapted the technology and is providing it to the world. Those are the kinds of opportunities we develop inside MIT Nano. This is just one of the views into the 10,000 square foot facility, 10,000 square meter facility that is MIT Nano. And there are many, many great opportunities within that we can still develop. We just started. We opened up the facility in August 2019. We celebrated the opening a year before, and we had a chance to celebrate it together with our colleagues from Monterrey Tech. The facility itself enables many different ways of depositing materials. I'm showing you here an unusual way of coating materials led by Dr. Jeremiah Mwara, which is a large area coating technology. Why? Because you can rethink the way you make solar cells or light emitters. Let me give you just a couple of examples of technologies that could be launched, and indeed have been launched through the uses of tools that are now inside MIT Nano. Let me show you this particular technology. This is a simple idea. It's a pickle that is electrically excited using 100 volts AC voltage, and that AC voltage causes electroluminescence of that pickle. If you slice that pickle very, very thin and apply 5 volts, not 100 volts, you can get electroluminescence of molecular species, and in this case, generate a technology known as organic light emitting technology, OLEDs. OLEDs are tens of billions of dollar industry right now. 20 years ago, they were not real. No one really believed in them. But today, they are likely going to replace all of the displays as we know it in a few years, a $120 billion opportunity through the use of nanotechnology. A very simple way of using electrically excited molecular species. What is missing for OLEDs to actually grow to the great technology that they are is and provide these great advantages of high contrast, super thin, ultra fast, pure color, incurvable TVs. What was missing is a large area nanofabrication technology, a tool, a machine tool, to allow us to actually make these displays precisely and repeatedly with high yields every single time. We at MIT spend a lot of time asking questions of what's the basic physics, what's the basic science that makes these kinds of displays work. But then we also take the next step and ask, technology is in my laboratory is a great thing to see, but not useful to the world. What's useful to the world is me being able to give that technology to the world, and the key to that growth is indeed developing tools that can allow us to scale such great ideas. Here's a tool that took about 6 years to build, 8 years to get into commercial production. It's a printer, and you can see the size of it. This is the small version of the tool. The bigger one is maybe 4 times bigger than this. The tool is called YieldJet and is designed for production of OLEDs with an extremely high yield. It's built by a little startup, Cativa, students that looked at the technical ideas they developed as graduate students and realized they can make them real if only they can come up with tools to allow them to scale the ideas. They needed to build this particular technology. It has parts from 1,000 manufacturers needed to be put together just right to make a system that then provided mass production. The particular tool that you see, I will go ahead and show you the actual operation of. This is a video of that tool. It is indeed printing molecular films over 2 meter by 2 meter glass substrates. It has 90 seconds to cover the entire area. It does so actually in 75 seconds in order to be able to give you very, very large TV screens. This tool now is used to make OLEDs of the world. If you have an organic LED screen on your phone, Android phones have organic LED screen. The latest Apple phones, Apple Watches have organic LED screen. Indeed, it's made on this tool. That first year, 100 million cell phones were made with this tool. Now it's 100 million cell phones nearly every month. And here is Jerry, one of my students, who started this technology together with 3 other students, as well as us professors trying to do our best to be useful and helpful to them. Jerry Chen recognized the opportunity, and the picture on the wall that he's pointing to, that is the small piece of glass his tools can handle. The big red line, that is the big piece of glass that his tools can handle. 3 meters by 3.3 meter substrates that need to deposit nanoscale thickness of films with a 5 micron precision over the entire 3 by 3 meter area, with a yield that makes every screen have every pixel working. You're allowed to have one bad pixel on your screen. Of the 4 million pixels, one subpixel is allowed to be not quite as good. But the others, every single one of them needs to be exactly the same. Your eye can pick out 3% difference between neighboring white pixels. So it better be that all of those pixels on your screen perform exactly the same. That turns out is a bigger challenge than has ever been done before in semiconductor industry. A typical chip that runs your computer has anywhere from 5 to 10% of its transistors not performing to the expected performance regulation. In these displays, the yield needs to be 99.9 something in order to go ahead and have a workable display. And go ahead and use semiconductors that have never been touched, these ones, to enable a market that now commands tens of billions of dollars of industry and indeed has a chance of capturing all of the $120 billion of display industry. That is the vision of where nanotechnology can take us in given time. And by the way, there has never been less than a decade of a journey from a brand new idea to a scale up that million people hold in their hand. So you need to have patient, long vision and great vision to where things are going in order to launch those next set of great ideas. What Cativa could do is envision where the world is going. They could imagine the next set of display technologies that indeed allows them to unfold their displays into large area displays. Now, mind you, this is what would be known as a shell cell phone. A cell phone that allows you to unfold your screen without a seam in the middle. The first time that you can see these commercially was last year. Actually, a year before, but the first versions didn't work so well. Second versions worked a little bit better. Cativa made this video about 6 years ago because they knew what the future is going to hold. They knew that it's possible to make these technologies using their tools. Let me show you another quick technology that indeed enabled another light-emitting technology to become. This is a technology of colloidal quantum dots, little chunks of stone that happen to be anywhere from 2 to 12 nanometers in diameter. Choose your material and choose the size of that material, and you'll be able to tune the luminescence of the material across the rainbow of colors. This is very powerful if you're looking at ways of making good light bulbs, as incandescent light bulbs look really good, but they're very inefficient. You know that because if you ever tried unscrewing a working incandescent light bulb, the heat from it burned your fingers, meaning it's a very inefficient light bulb. It makes a lot of its energy in the form of heat, not light. LED lights are really good energy-wise, but their color is not always desirable. The red colors are missing from their spectrum because they're based on gallium nitride blue LEDs. And the optical down conversion from blue to red is typically inefficient until we introduce the quantum dots inside the down conversion system. At that point, you can generate a light bulb that when you illuminate a bowl of fruit with, you realize your bananas now look just as good as they should under the incandescent light bulb. And yet the amount of energy you're expending is 5 times less than the incandescent light bulb. Hence, you can generate the light bulb that is much more efficient and yet of the same color quality. This was a good business when the technology was introduced back in 2009 and the LED lights were of significant cost. But when the LED lights started dropping in their cost, the fraction of that cost goes to the quantum dot optic that was not very much money as the LEDs became cheaper and cheaper. So the key for the success of this particular idea is to recognize that there is another light bulb that's needed, and it's more expensive and more difficult to make. This particular technology made by QD Vision took the quantum dots, made the light bulbs first, and then made the TV light bulbs. Light bulbs that were designed to serve as edge-emittive light on a liquid crystal display, and have shown that you can transform a typical liquid crystal display with a quantum dot light bulb in the back into a much, much better looking TV. This particular opportunity led to an acquisition of QD Vision by Samsung, and what you can now buy in the stores is Samsung QLED TVs. This is the flagship product of Samsung when it comes to TV technology. Quantum dot enhanced LCD screens enabled by the optical down conversion of light and quantum dots participation in the generation of light. Technology initially envisioned in the laboratory and now on a shelf and used by millions. Again, the journey typically takes 10 years to grow that idea. But those 10 years dramatically multiply the impact. The best ideas, just like good wine, takes time to age and takes time to perfect so they can be given to millions as exquisite products. Let me show you another direction. So power used now by the planet is on the scale of about 16 to 18 terawatts. Sun provides us about 10,000 times more power than that. There are not quite, but almost 10,000 hours in a year. So if you could collect all of the sunshine in a course of an hour, we will be able to power the planet with that energy for 1 year. That's a remarkable statement from perspective of the energy availability to us. There is a challenge in the way that I presented a problem. I told you we would like to catch all of the sunlight's power in 1 hour so we can power the planet for 1 year. One challenge is that, well, we would need to cover half of planet Earth with solar cells, the half that's facing the sun for that 1 hour. That's a lot of area. So maybe we can cover 1% of planet Earth with solar cells. Oh, well, then we'll need about 100 sunny days with 100 hours of sun collection. And that is if the cells are 100% efficient. Well, let's say cells are 10% efficient to make our calculation simple. Well, then we'll just need about 1,000 hours in the course of a year, still with 1% coverage. And we'll be able to provide all the energy we need as long as we have storage available as well. Solar is a grand opportunity. And the technologies that are coming to us through the large area nano manufacturing over very, very thin large area substrates will enable us to deploy them in entirely new ways. Typical solar installation might look something like this, with big photovoltaics covering your roofs, typically made of silicon, hence why they're dark blue, and why you might need to reinforce your roof to carry the weight of the heavy cell. A silicon module weighs about 50 pounds. That comes out to about 22 kilograms, 25 kilograms. That requires you over larger area for 2 meters, 25 kilos. For, 50 meters of solar cells, that's a lot more kilos, and hence why you need to reinforce your roof. But silicon is not the best material to absorb light. It's an indirect bandgap semiconductor. And the opportunity is to ask, well, what other emerging films are there to allow us to make large area solar in extremely thin formats? Silicon is heavy, not because of silicon. Silicon wafers are not very heavy at all. They're about 1.5 thickness of human hair, typically. But because of that, they're extremely brittle. They break very easily. And so you need a 3 millimeter, 4 millimeter piece of glass that sits behind your silicon cell to prevent the cell from getting bent, and as a result, prevent it from cracking, as it's very, very brittle. Opportunity, hence, is to figure out, well, how do I make an extremely thin cell? Because the thinner the cell, easier is for me to bend it, and I'm not going to have to worry about it being curved. Why is that? Well, it's kind of like us standing on Earth. Earth is curved, but we are so short compared to the Earth that we don't notice the curvature. In the same fashion, if I give you a very thin cell and I bend it, that macroscopic bend will not be observed or felt by the molecules that make the cell. Give me an extremely thin cell, and I'll be able to give you an extremely lightweight substrate to sit behind it, and hence make rollable, roll-to-roll, stretched, extremely lightweight cells. Solar opportunity for what's coming is in lightweightedness, and hence production of it might be as simple as printing newspaper out of abundant materials, extremely lightweight so that they can be easily deployed. And indeed, at MIT Nano, we do that. This is a video of a material being printed. This is so-called perovskite materials, printed in a matter of minutes over 100-meter-long substrates. There is Richard, one of the students working on this project, holding a cell, and indeed, his colleagues in a related project reached the world record in performance, 25% power conversion efficiency. That number has been since improved. This was a record last January, February. Over the summer, I believe the number is now 25.6%. But whatever the number, what really, really matters is the weight of that cell. Even if much less efficient, even if it's only 10% efficient, if I can reduce the weight 100 times, and I can, I'll make a much more valuable technology for deployment. Here's a version of that cell stretched on that roll. It's 100 meters long. And you can make it printed, not just on plastic, but extremely light paper, if that's what you wish. There's a potential for nearly free electricity, nearly free energy, if you use such lightweight cells, because if you can reduce the weight, make it light, flexible, rather than racking cells on your roof, you can simply unroll them. And as such, generate an extremely simple way to install over very large areas your solar panels. This could reduce the cost of electricity by a factor of 3, reaching nearly 1 cent a kilowatt hour. The electricity in Massachusetts, where I'm right now, is about 16 cents a kilowatt hour. This can dramatically reduce the cost of energy and provide it on any surface you touch. Most importantly, there are nearly 1 billion people out there without access to grid electricity. For them to get electricity to their remote areas of the world means carrying your cell on someone's back. Well, that's fairly hard to deliver, as there are no paved roads to drive the cell to the village. Individual carrying that cell does not care what is the efficiency of the cell. They only care about watts per kilogram. How many trips will I have to make to electrify my village? Because I can only carry so many kilos on my back over the long distance I need to walk. And that is now possible to do. Here's a version of that cell made on a piece of paper. When you shine light on it, you actually are powering the clock using that very simple piece of paper. This cell is flexible and durable enough. It can pass through a printer. You can print right on top of it if that's what you wish. Attach it now still to the electrodes, shine light, and that clock will still work. Your technology, indeed enabled entirely through the use of a piece of paper and some nanostructured materials painted on top. Transformative way of thinking of what cell can be. How light can you make it? You can make it so light that you can rest your cell on top of a soap bubble and wait for it to sit there. Indeed, the soap bubble will not even notice that the cell is there. This is an extremely lightweight cell. This cell is about 1/20th the thickness of human hair. Indeed, it generates 6 watts of power per gram of the cell, or 6 kilowatts per kilogram, over 100 times more power than what silicon gives you per gram. Now, you might want to have cells that look a little bit different than the ones I just showed you, because you might not like the color of my cells. At which point we can offer you, through the use of nanotechnology, a cell like this. This is a cell that is invisible. It's designed not to absorb visible light, so you can look through the cell, but does absorb infrared light. And in this case, the cell with sunlight shining on it generates 106 volts and microamps of current as the cell is being powered by the sunlight. It's the infrared and UV light that it catches and lets the visible light through, allowing you hence to make a device like this. This is a solar cell, and you can attach it to the electrodes, provide enough infrared light in the environment, and you'll generate electricity needed to run that motor. That cell operates by using energy that we do not need for visible experience. Hence, it can be installed in Windows. And indeed, another little startup, Ubiquitous Energy, looks at ways of doing exactly that. These are about 0.5 meter by 30 centimeter windows generated in their prototyping facility in California that allows them to then outfit their own offices with these solar cell windows, hence providing you power without you even knowing that you're looking at the solar cell. You can put it on your glasses, you can put it on an e-reader, or you can put it on skyscrapers. An e-reader with a transparent solar cell as a screen would never need to be charged again, because the power obtained in the course of your reading would be enough to trickle charge your battery, and as a result, never need to be plugged into a wall. That would truly enable the Internet of Things. It could truly change the way we relate to our technology by providing ubiquitous power on any surface without you even knowing that that's where the power resides. There are many, many, many markets that one can imagine this technology being in. But the key is to make the first beachhead prototypes that allow you to rethink where technology can go. And that is the purpose of MIT Nano, a facility that we see sits at the dawn of the nano age and open to anyone who wishes to use it, and most importantly to our partners and colleagues from institutions like Monterrey Tech that work very, very closely with us. We placed MIT Nano in the heart of MIT campus. MIT campus, you might know, is a interconnecting set of buildings that each one of them makes an easy access to any space of MIT. And MIT Nano is right there at the center, serving anyone's needs. It's designed to boost innovation by bringing people together of different disciplines who can easily encounter each other, and most importantly, who can engage each other after they meet, who can ask questions and curiously pursue new ideas together. It's a space that has in it an ability to accommodate over 1,000 users in the course of a year. Today, and in the last year and a half of being open, we engaged 490 users in our fab, about 100 users in our characterization capabilities, and we're growing. The space of MIT Nano is broad. It does enable us to go over many, many, many opportunities. And indeed, it brings in the greatest of users that go through our clean room facilities, our characterization facilities, and our prototyping facilities. These are the scholars from Monterrey Tech that are standing on the 5th floor of MIT Nano in front of the Tecnológico de Monterrey prototyping facility, are indeed ways of honoring our relationship, long-lasting relationship with our colleagues from Monterrey Tech, and honoring Mr. Garza, a graduate of MIT of the class of 1916, who saw the vision of technology as being the key to the advancement of the next set of world's needs, and hence started Monterrey Tech. We are honored to have a chance to call him as part of our alumni. What disciplines are particularly important at MIT and at MIT Nano? Well, nanotechnology spans nearly everything we do. About half of our young professors in the School of Science and about 2/3 of our recently tenured professors in the School of Engineering use nanoscale to make their advancements. Now, why do I tell you only about the young professors? Because those professors are the future of where the world is going. It's the youngest of the professors that define where the future will be. And they are working on medicine, life sciences, energy systems, computing, manufacturing, materials, new structures, quantum science, technology, and education, preparing the workforce that will then be able to step into the industry and transform the world through the knowledge they gained at the academic institutions that had hands-on experiences that were meant to foreshadow where the world is going. That's what MIT Nano is about. Impact of MIT Nano is broad. And I'll just enumerate it through this particular program we are very proud of. Our Tech MIT academic program that fosters the careers of young engineers and scientists in Monterrey Tech. Initially, we are focusing on nanoscience and nanotechnology, broadly construed, across all of those disciplines. Undergraduates come for summer research internships. Graduate students stay with us to do their research work. Postdoctoral fellows, as well as junior faculty stay. As well as we offer short courses in nanotechnology. Last summer, over 100 participants from Monterrey Tech participated in those courses. Impact, many publications. Well, how good are those publications? They are remarkable. This is a plot of joint publications by Hector Caballos. He has pointed to us the fact that the impact of MIT publications and impact of tech publications when we work alone is not as good as the impact of the publications published jointly when we work together. Highly cited papers, more cited than average MIT papers, and high representation in the very top journals. That is the success of collaborative interactions. Here are the present visitors of tech that are at MIT. They are exploring multitudes of fields in electrical engineering, in the microsystems areas, in mechanical engineering, in biology. They span the disciplines of MIT just like they span the disciplines of tech. And they're a part of a much larger group of scholars who we had the privilege, again, of sharing MIT Nano with. These are scholars that will launch entirely new ideas that will allow us to go from academic discovery into grand opportunities through the development of new startup ideas that will then be able to be absorbed by industry, that will be able to grow and build a better world. I will stop there. I thank you very, very much for your attention. And given that we have maybe a few minutes, I'll be delighted to take a few questions. Thank you again.
Thank you so much, Vladimir. And I think that we can start with some questions. So I think we have time for one or two questions, and I will start in order. So the first is, do you think that it's possible that in a near future, with nanotechnology, we will substitute the actual vaccination methods?
Nanotechnology already has allowed us to have the discoveries we have today. The Moderna, right, Pfizer vaccines are the nanotechnology recognitions from a decade ago growing into extremely rapidly deployed new medicines. I would point that the aspirin is a nanotechnology. And indeed, we have been using medicine, nanoscale power of medicine for many, many years. The difference now is that we actually can do it predictively. We understand why things happen the way they do down on nanoscale, because finally, over the last decade, we finally have the tools to be able to see what truly happens. There are still many, many mysteries that we need to unlock. But given the present track record, even with the very beginnings of our discoveries being so powerful, I can only imagine the power of the future medicine that's coming our way.
Thank you for that answer. And another question will be, what is the actual status of the regulations about nanomaterials, for example, for food, cosmetics, medical devices, and drugs?
You're asking a fantastic question, because nanoscale, because it's so small, acts on us in positive or negative ways. Ibuprofen and aspirin are good examples of nanoscale items that act really well on us, providing us the cures. LSD and cocaine are also nanoscale items that don't act on us quite as well. Being able to understand the consequences of the use of particular nanoscale items is really important, but we are surrounded by nanoscale. Anytime we use detergents, we're using nanoscale molecules to clean our clothes or generate glow of white laundry in sunlight, and hence generate whiter than white clean clothes. Anytime we use perfumes, we're using nanoscale. Anytime we eat food, we are using nanoscale. Our shirts don't wrinkle anymore because we use nanoscale fibers. Our pants don't get stained when I spill ketchup or barbecue sauce on it because there's a nanoscale coating on it. Nanoscale is present all around us, and introduction of the next technology, nanoscale technology or macroscale technology, always will require tests before being more broadly adapted. It's a great question, but we shouldn't fear nanoscale any more than we fear any other new technology that we bring in.
Thank you. So nanotechnology is everywhere. So one last question is, how could nanotechnology impact in Industry 4.0?
Well, it already is. I showed you the example of Cativa, which is a company that started from a very simple idea of printing nanotechnology in a controlled fashion and has revolutionized a multi-billion-dollar industry through it. This is one of many, many examples that I could cite through the work of MIT. The directly printed materials through the 3D printing of plastics or metals is about to change the way we think about how we fabricate new material spaces. There is many opportunities in electronics, in mechanics, in medicine, new ways we do quantum computing. All of them are enabled in the way we do nanoscale. I mentioned C2 Sense as a way of detecting ethylene or ammonia or other analytes in the air. That is nanoscale being used in the macroscale application. It's the nanoscale over macroscale areas that will be the key to the next deployment. And that's why I highlighted the opportunity to think about very large area coverage like solar that will completely redefine what a solar cell look. My guess would be in 5-10 years from now, silicon will be a thing of the past. Just like we don't use vacuum tubes anymore, we use transistors. Actually, we don't even use transistors. We use integrated transistors, integrated circuits. In the same fashion, we'll be looking at today's silicon PVs a few years from now and say, that's like vacuum tubes of the past. Because the new technology of solar of 10 years from now, 5 years from now, will be manufactured through the new tool sets and new materials by the industries of today that have long enough vision, long enough expectation to capture entirely new markets.
Well, thanks again a lot for your time and for this awesome conference that we just heard. And thank you also to the audience for being here. And please continue to check the program of the Congress. And thank you again, Vladimir.
Thank you, Adriana, and thank you to all that are attending the conference. It's an honor to be with you.
No, it's an honor for us to have you here. Thank you.